We're going live, and we're not live. All right. So welcome to Chapter 8. Okay. So this will be fun. The weird thing about a sequence is some people love them and some people hate them, and I don't know. It's hard for me to predict who will like them and who will hate them because it's just weird. But anyway, we're going to talk about 8.1, which is sequences, and summation notation. Okay? Now, you can probably already figure out that I can come up with a sequence 2, 4, 6, 8, 10, etc., right? Or I could come up with another sequence 5, 10, 15, 20. I'll bet you guys could tell me what the next terms in those sequences. Oh, we're not on. Oh, what is that? Out of focus. Focus, would you? Oh my gosh, that's terrible.
You still say focus.
Yeah, there we go.
Oh, it worked.
Okay, so yeah, we need to focus like we did in the last chapters. Okay, so you guys can recognize these are sequences. I'll bet you that Hunter, you could tell me the next term in this sequence would be, and Victor, the next sequence in this one would be. You can totally recognize those as sequences. So one way we might identify these, the first term we would represent with a sub 1. The second term we would be a sub 2, a sub 3, a sub 4, etc., right? So these subscripts are just telling you this is the fourth term in the sequence, or the second term in the sequence, or whatever. Does that make sense? Okay. So these are just some common sequences. We'll get into some more uncommon ones. And then we might say, for example, find a sub n, where n represents a number, such as a sub 100. That one might be a little bit harder to figure out right now, but you could probably figure it out if you just counted out 100 terms, right? Okay. We'll try to find some formulas so we don't have to guess what a sub 100 is here. Okay. So let's do some sequences where I say a sub n equals, and then I'm going to give you a formula, 2n minus 1. And I'll say find the first 5 terms of this sequence. Okay? So, in this case, I want to find a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. Okay? So, in this case, if n equals 1, Angel, if I'm using this as a formula, this becomes 2 times 1 minus 1. 2 times 1 is 2 minus 1 is 1. Okay? Berkeley, a sub 2, what would I do?
2 times 2 minus 1.
So 2 times 2 is?
4.
4 minus 1
3.
would be 3. A sub 3, a sub 3 would be what, Sam?
2 times 3 minus 1.
2 times 3 minus 1 equals 5. A sub 4, Christian?
2 times 4, 8 minus 1, 7.
Times 1 equals 7. And a sub 5, Kelly?
5 times 2 is 10 minus 2 is 9.
Equals 9. And so you see a sequence here. What does this sequence look like? Prime numbers? Odd numbers, right? So this might be a sequence for odd numbers. Okay? So that's how you could mathematically represent all the odd numbers. Okay, let's do another sequence. What if I said c sub n equals c squared, no, m squared minus 1. And I say the same thing. Find the first 5 numbers in the sequence. Okay? So if this were my sequence, Hunter, what would be the first term?
1 squared minus 1,
Which is 0. Ethan? Seconds. term in the sequence? 2 squared minus 1 equals 3. Third term in the sequence, Cameron.
3 squared minus 1.
3 squared minus 1 equals 8. Fourth term in the sequence, Victor.
4 squared minus 1.
4 squared minus 1, which equals 15. And the fifth number in the sequence, it must be Caitlin's turn. I want to make sure she's paying attention. Caitlin, what would be the fifth sequence in the term?
It would be 5 squared minus 1?
Which would equal
24.
24. How many of you like these questions on the test so far? These aren't going to be too bad, right? Okay. Let's see if we can do them a little bit harder here. How about t sub n equals n over n plus 1? Find the first 5 terms. Niels, what's t sub 1?
Be 1/2.
1 over 1 plus 1, which equals 1/2. T sub 2 equals what, Jonathan?
2/3.
2 over 2 plus 1, which equals 2/3. T sub 3 equals what, Bailey? 3 over 3 plus 1, which equals 3/4. T sub 4 equals what? We're back to Angel again. We're going to go through the class quickly, I can tell. You're going to get picked on 5 times today. 4/5. We're going to dispense with the easy stuff. T sub 5, Berkeley.
5/6.
5/6. Okay. These aren't too bad. How about one more? Oh, I'm off the screen. You guys are supposed to warn me about that. Okay, here we go. R sub n equals -1 to the nth power over 2 to the n. This one's going to be a good one, I can tell. Sam, what do you think? What's R sub 1?
So it's going to be -1 to the first power over 2 to the first power.
Which is going to equal.
-1/2.
Okay. R sub 2 equals, Christian.
So -1 to the second power over 2 to the second power is 4. So it'd be 1/4.
1/4. R sub 3 equals what, Kelly?
It's going to be -1 to the third over 2 to the third. And it's going to be -1 over 8.
8. R sub 4 equals, Hunter, it must be your turn.
-1 to the fourth power over 2 to the fourth.
Okay. 1/16. R sub 5 is what, Ethan? -1 to the 5th over 2 to the 5th. So that's going to be
-1 over
32. Now, do you notice that these alternate in signs? Okay, goes negative, positive, negative, positive, negative, positive. Okay, so if I give you a sequence and it needs to alternate signs, this is a really good way to get you to alternate signs. Okay. All right, not too bad still so far. Okay. All right, so let's talk about let's see, can you do it in reverse? Okay. What if I said, what if I give you a sequence? Can you come up with the formula? Hopefully these aren't too bad. What if I had, oh, thank you. What if I had 1/2, 3/4, 5/6, 7/8, comma, dot, dot, dot. Do you think you could come up with a formula for that? Now I erased it here, but do you see the numerators are all odd? Okay. For those of you who are keeping notes, what was the formula we used for odd numbers?
2n plus 1.
2n minus 1. So that could be your numerator, right?
Just do 2n.
What would be a good formula for even numbers? 2n. Okay? So those would be even numbers. So this could be a sub n equals 2n minus 1 over 2n. Okay? Not too bad so far. What if I said, what if this was my sequence? -2, 4, -6, 8, -10, etc. Could you come up with that? Caitlin?
Okay,
We've got alternating signs again, right?
yeah. So would it still just be the 2n thing or not?
So we've got, so even numbers would be the 2n thing, but that's not going to alternate signs. So how could I alternate signs?
I want to say plus or minus, so that's right.
Okay, I don't want to put just plus or minus. How did we do it on that last problem?
Was it under negative 1?
I could multiply by -1 to the nth power.
Oh, okay, that makes sense.
Now let's make sure that works, because sometimes you want to n, sometimes you want to n plus 1. Okay? So my first term, if I'm checking this, let's assume that this is correct. I'm not sure if it is, but let's pretend it is for a minute. If n is 1, this becomes 2 times 1 to the -1 to the first power. So that's going to be 2, and it's going to be negative. Is that what I wanted?
Yeah.
It is. Let's make sure that the second term works. 2 times 2, -1 to the second power. 2 times 2 is 4, -1 to the second power is positive.
So yeah.
So far.
Okay, so
Okay? Check one more just to make sure. A sub 3, 2 times 3, -1 to the third power. So that's going to be 6, and it's going to be negative. It matches. Okay? I know you guys are all too young to remember the $6 Million Man, right? Anybody ever see that show?
I've heard of it, but I haven't seen it.
Oh my gosh, that was a great show when I was a kid. But can build it. It's about. So Steve Austin, who was lead majors in real life, was an astronaut. He crashed on the moon, was badly damaged. They said, okay, we're going to build bionic limbs for him, and then he became this super strong, like almost incredible Hulk, although he didn't Hulk up. He just could lift anything super fast, like a robot man.
Wait, is this true?
Yeah. Was it true? No, it was not true. Yeah, it was a great show in the 70s stuff. Okay? So we can build it better than ever. Okay? All right, so let's talk about, okay, a recursive sequence. Recursive. Okay? And the idea behind recursive is the sequence depends on the previous term. Okay? So let's say that, so let's define that a sub 1 equals 1. And then a sub n equals 3 times a sub n minus 1. Am I writing this right? Yes, I am. N minus 1 plus 2. Okay? So the idea here is your current term depends on your previous term plus 2 multiplied by 3. Okay? So if you're doing a recursive sequence, you're always going to have to define the first term. And then the rest of the formula depends on the previous term. Okay? So in this case, a sub 1 equals 1, because I defined it that way. A sub 2 is going to equal 3 times the previous term, which a sub 1 is 1, plus 2. In this case, 1 plus 2 is 3 times 3? 9. Okay? A sub 3 is what, Victor?
3 minus
3 times, what's your previous term?
3.
Your previous term is 9
Okay.
plus 2. 9 plus 2 is
11.
11 times 3,
33.
33. A sub 4 in this case is what, Niels?
3 means 33 plus 2.
33 plus 2 is
35.
35 times 3, 105. We'll stop there. I don't want to keep going. I'm not a mathematician. Okay? But we can write the formula, even though I can't do that in my head. A sub 5 would be what, Jonathan? Wow, you did that in your head that fast? Are you a mathematician?
I just
Okay.
started it as soon as you finished.
You started it as soon as I finished the last one. But how would we figure it out?
Okay, 105.
3 times 105
So
plus 2.
107.
3 times 107 is,
What?
what'd you say?
Yeah.
321.
3 times 7 is 21.
Yeah, that wasn't too bad, I guess. Okay? All right, so that's how you would define a sequence recursively. Now, there is a very famous recursive sequence, and it's called the Fibonacci Sequence. Okay? Okay, and here's how the Fibonacci sequence works.
Oh, you're just on screen.
Oh, am I off screen? Okay. Barely, here, let's pop that up a little bit. Okay, Fibonacci sequence. It's defined a sub 1 equals 1. It's also defined as a sub 2 equals 1. And then a sub n equals, let me make sure I get this right. A sub n minus 1 plus a sub n minus 2. So it's a recursive sequence that depends on the previous two terms, not just the previous one. Okay? So a sub 3 in this case would equal what, Bailey? One way to think of it is, if this notation bothers you, write it just as a sub 3 minus 1 plus a sub 3 minus 2. This is a sub 2, right? What's a sub 2? It's 1. What's a sub 1? 1. So a sub 3 equals 2. A sub 4 equals, whose turn is it now? I guess, did I go through everybody? I feel like I skipped Cameron.
Sure.
A sub 4 is what?
Would be a
A sub 3 plus a sub 2, right?
Yeah.
Okay?
Oh, yeah.
It's the previous two terms. So a sub 3 is
2
2 plus a sub 2
is 2 or 1.
1.
Yeah.
So this equals
3.
3. A sub 5 equals what, Kelly?
It's gonna be a sub 4, which is 3.
A
Plus,
sub 4 is 3 plus
2.
2 equals
5.
5. Finally, a sub 6, we'll stop there. Christian is?
So when you're doing this, are you breaking it up to match the two ones at the top?
Am I breaking it up what?
Well, so like with the one I just do with 5, you do 4 and 3.
Yeah, I skipped a step. So a sub 5 minus 1 plus a sub 5 minus 2.
Oh, so
5 minus 1 is 4, 5 minus 2 is 3.
Okay, so for this one you're just doing a sub 6 minus 1.
a sub 6 minus 1 plus a sub 6 minus 2, correct?
Oh, okay.
Okay,
That turns into a sub 5 plus a sub 4.
equals a sub 5 is
5,
5 plus
3.
3 equals 8. Okay, so your sequence goes 1, 1, 2, 3, 5, 8. Now it's scaring me that I'm getting so old, but there was a famous movie with Tom Hanks where that had a Fibonacci sequence in it.
Was that Da Vinci Code?
Da Vinci Code had a Fibonacci sequence in it. Okay?
It was a book before it.
It was a book before it was a movie, before Tom Cruise was in it. Did you guys read the book?
Angels and Demons was better.
Oh, I like that first one better, but Angels and Demons was okay. But it just got repetitive after a while, didn't it? Okay? So anyway, there is another, so the Fibonacci sequence, I'm going to show you this because I think it's pretty cool. There is a temple in Independence, Missouri. Where, pictures, images. Okay, this is it. Okay? And hopefully we can see that on the camera. I don't know if we can see it. Oh, you can't see it. Okay, so if you see this spiral temple here, spiral shaped thing, that is actually a Fibonacci sequence.
Oh, yeah, it's all over in nature, I just remember now.
Say it again?
It's all over nature, like.
It's all over in nature. So the conch shells, a lot of those are Fibonacci sequences. Can you see inside? The inside of it's really cool too.
Inside of it's just like
Why don't they have anything on the inside?
like smash it down. So it's just like
I think there was one on the last page. This is kind of in it, but it's, yeah, I don't know. We'll see if this actually has the inside of it. Oh, nice. We got a nice commercial there about Jeffrey Epstein. Awesome. Okay, so yeah, this is the Community of Christ Temple. It's really cool. I've actually been there, but it is totally based on a Fibonacci sequence. And 300 feet in the air, you can't miss it. Hurry up. I want to see the inside.
I mean, you can make it go faster.
Oh, there's the Oregon. Oh yeah, here we go. Okay, here we go. So this is looking up into the spire. There you go. That's the inside. That's pretty cool. So, yeah. Anyway, so really cool if you get a chance to go out there. All right. So there's your mathematical Fibonacci sequence for today. All right. So that's the most famous recursive sequence. You can see there on page 596. They've got the Nautilus shell there. And that's what that temple is supposed to look like. It's based on that same thing, the Nautilus shell. All right, so one of the things that we like to do is find the sum of sequences. Okay? So if I had a sequence, so typically we use the letter S for sum. And let's say I had a sequence 1 over 2, 1 over 4, 1 over 8, etc. And I said find the sum. So S of 1 would equal the sum of the first term. Sum of the first term of this sequence would be 1/2. S of 2 would be S of 1 plus S of 2. The sum of the first two terms would equal 1/2 plus 1/4, which would equal 3/4. The sum of the first three terms would equal sum 1 plus, or sum 2 plus the sum 3. I really shouldn't use s, but anyway, the first three terms. So this would be 1/2 plus 1/4 plus 1/8, which would be 4/8 plus, let's see, 2/8 plus 1/8 would be 7/8, correct? Okay. So a lot of the times, we will write the sum of sequences with the Greek letter sigma. Okay? Now, I know that looks kind of like a weird looking E. It's actually the Greek letter sigma. And what you could do is you could get a sequence such as, let's say that I had a sequence 1 over n minus 1 over n plus 1. And I wanted to do it from, let's say that I would say that n equals 1 to 4. Okay? So in order to do that, let's figure out what the sum of the first 4 numbers would be. So we'll have to find the first 4 numbers before we can actually find the sum, right? So Angel, can you help me find a sub 1 in this case?
1 over 1.
1 over 1 minus
1 over 1 plus
1 over 2. So 1 minus 1/2 is 1/2. A sub 2, Berkeley. So we're using this as our formula.
Oh, okay.
What's the second term? Okay, so n equals 2. If I put a 2 here, that becomes
Okay.
You're ignoring the whole sigma side.
1/2. I'm ignoring that for a moment, but we'll get to it in a minute. I have to find the first force before I can add it. Okay, so 1/2 minus
3, 1/3.
1 over 3. So that's going to be 3 minus 2, that's 1/6, right? A sub 3 in this case would be what, Sam?
1 over 3 over, or minus 1 over 3 plus 1 over 4,
4.
which is
So
equal
it's
to
4.
1/12.
Minus 3 is 1/12. A sub 4 would equal what, Christian?
1 over 4.
1 over 4 minus 1/5. So that would be 5 minus 4, which would be 1/20th, right?
Yeah.
Okay? So the sum from n equals 1 to 4 of this sequence, 1 over n minus 1 over n plus 1, would equal simply the sum of these first 4 terms, correct? So 1/2 plus 1/6 plus 1/12 plus 1/20. Okay? Is that easy? Nice and easy?
Yeah, sure.
Okay? All right. Okay, so let's keep going here. What if I said, find the sum from k equals 1 to 5 of k squared. Okay? So, Cameron, how would you do that?
You do k of 1,
So,
right? Because you have to find what
a sub 1 would in this case would equal
1 squared is
1 squared, which equals 1. A sub 2,
2 squared,
2
4,
squared equals 4. A sub 3,
9.
3 squared is 9. A sub 4,
Let's see, 16,
16. A sub 5,
25.
25. So we can add those up. 25 and 25 is 55, right? So this would equal 55. That make sense? Okay. What if I said, I want the sum from j equals 3 to 5 of 1 over j. How would you do that one, Kelly?
You would have to find J of 3, 1, and 5.
Okay? And J of
Or
3.
ace of 3.
Yeah, so this would be 1 over
3.
3 plus
1 over 4.
1 over 4 plus 1 over 5. And when we get our nice common denominator, we would easily get 47 out of 60, as everybody knows, right? Okay? All right, how about the sum from k equals 5 to 10 of k? Hunter, it must be your turn. This would equal what? 5 plus 6 plus 7 plus 8 plus 9 plus 10. That would be 19, and 8 is 27, and 7 is 34, 45. Right? Okay? Now, this one's going to be the trick question, yes.
That one on the bottom there, so was it 5 terms? Is that a 5 or?
You're starting it.
I started at 3 instead of 1.
Oh, okay, so you're
Yeah,
going.
you don't have to start at 1 all the time. Okay?
Oh,
What do we find right now?
Yeah, I started at 3. Okay, how about this one? This one's going to be a tricky one, and then you'll be like, oh, duh. I equals 1 to 6 of the sequence 2. Okay? What do you think, Victor? What's your first term?
2.
Your first term is 2. What's your second term?
2.
Third term?
2.
The fourth?
2.
Fifth?
2.
Sixth. So 2, 4, 6, 8, 10, 12. Okay, does that make sense? That was easier than it looked, huh? Yes.
Could
Yes.
that also be written as 2 plus number to the 0 power?
2 plus number to the 0 power. I guess it could. Is that right? No, because that would be
No,
3 every time.
Could you just do 2 times the
I guess you could do 1. 1 plus number to the 0 power, right?
Yeah.
Because that would be 2 every time. Or you could just write 2. Okay, question, Kelly?
Oh, I was gonna say, couldn't you just take that number with like 2 and just times it by the top?
You're starting to notice some patterns here. We're going to talk about those patterns. Is it time to talk about those patterns?
Yes.
Almost.
Okay.
Yes, but you're noticing patterns here. And there are going to be some patterns here, and we got some formulas for you to remember. Can you do it in reverse? What if I said, and I want you to write in summation notation, that I have a sequence that is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, etc.
Yes.
Okay? Can you write that with a sigma? Whose turn is it now? It must be Ethan's turn. What would be the formula for this sequence? Can't hear you.
End of the third.
N to the third. Okay? And we refer to this as the index. So n equals what? 1 to infinity. Okay? All right, how about this one? What if I had the square root of 3 plus the square root of 4 plus the square root of 5 plus, and then I went up to the square root of 77. Now, there's actually lots of ways to do this. Pick one. Niels.
All right, so I'm going to draw the sigma
Sigma,
of the square root of n.
square root of n.
And then below the sigma, n equals 3.
N equals 3
And about 77.
to 77.
No, because this is the square root.
Oh, yeah, I see what you mean, yeah, okay.
So that would be one way to do that, and that would be correct. Is there another way to write this?
Top.
Square root of 77, get rid of the square root of n.
What'd you say?
Get square root of 77 and get rid of the square root over the n, right?
Get rid of the square root. I don't want to get rid of the square root. That's part of the sequence.
Okay.
Okay?
I like that better.
You like what he did better, Niels?
Could you flip the 3 and the 77? Can you go backwards in the sequence?
Could you? We don't normally do that.
It'd be weird, yeah.
We don't, I'm gonna,
But no.
is there a rule? I've never seen that.
I can do
Because we're doing
I've
addition.
never seen that.
We're doing addition so that you get the end result.
Yeah,
right?
theoretically, but typically you're going in increasing order. Could you rewrite this in another way that would also be correct? So for example, could you start at k equals 1 to 75
And then
of the
plus
square
2.
root of
And plus 2.
k plus 2, right?
Okay.
That would be another way to do it. These are equivalent, right? Or I could go from 2, k equals 2, or n, or whatever, I don't care what number you pick, 76, right? And this would be square root of
K plus 1.
k plus 1. Okay, so these aren't necessarily unique, which makes grading them a little bit more challenging. But I like what Niels did first. Yes?
So is there like, it doesn't really matter, or is it like typical to start at your first term where you would, typically you're gonna see it as the k equals 1 over.
So typically we do start at the first term, but I think in this case, this makes more sense. Okay? Yes.
So I'm just comparing to that one, so the j equals 3, so you start at 3, and then 3, 4, 5, so that's 3 total.
Yeah, we've got 3 terms here. 3, 4, 5 is 3 terms. 1, 2, 3.
Why is that 177?
We started, there's 70, how many terms are there? There's 75 terms. I can go from 1 to 75 or 3 to 77. Either way, there's still 75 terms. Okay?
Yeah.
All right. Okay, so we're now going to go to Kelly's. Kelly was jumping ahead of us. We're going to catch up to Kelly now. Okay? So let's talk about properties of sums. And we'll start with the first one, okay? So Kelly noticed that if you have the sum of some constant c times some sequence a sub k, you could, from k equals 1 to n, you could take the constant out and then just do the sum of the sequence. K equals 1 to n. Okay? That's kind of what we did right here. Okay? Slide that over so you can see that. Another properties of sequences says, if you do the sum from k equals 1 to n of sequence a sub k plus sequence b sub k, you can break that up, and that will be the sum from k equals 1 to n of a sub k plus the sum, these are getting away now, of b sub k from k equals 1 to n. Okay, so you can kind of think of that as distributing your sum through. That's perfectly legal. Yes?
Just to clarify on the first one, it is on the right side of the equals there, is that c supposed to signify it as multiplying?
Yes,
Sequence?
as multiplying.
As if it was inside parentheses and factored it out.
Yeah, you could think of it as factoring it out. Yes, exactly right. Okay, C is a constant, some sort of constant. Okay, like 3 or 7 or whatever you want to do. Okay, these are going to become very helpful in section 8.2. Rule number 3 says this also works from k equals 1 to n if you do subtraction. A sub k minus b sub k equals the sum from k equals 1 to n of a sub k minus the sum from k equals 1 to n of b sub k. Okay? So those are some properties you will want to know by tomorrow. Okay? All right. So that's the end of 8.1, yes.
What would be the motivation to split the sum?
Very good question. We're going to answer that in 8.2.
Okay.
Okay? Or maybe we won't. We will. I think we will. We'll see. All right. Okay, let's move on to 8.2. I don't know if I'll answer that today, but I'll do it on Monday. Well, Monday is no school. It might take me a week to answer your question.
No, we can still come in Monday.
You can come in Monday, but I won't be here.
Extra credit?
I'm going to give you the next week off. How's that?
Cool.
Isn't that nice?
Very thoughtful.
Well,
Oh, thank you.
what do you got?
Okay, just remember that when you do rate my professor. Okay, I'm giving you a whole week off next week. Okay. All right. Okay, so 8.2, we're going to talk about arithmetic sequences. Okay. So they are given by the definition a sub n equals a plus n minus 1 times d. Okay. Where a, in fact, I'm going to put a sub 1 because that's better. The book has a, but usually most other books put a sub 1. It's your first term, and so d equals the difference. Okay, that's the definition of an arithmetic sequence. Okay? So, if a sub 1 equals 2 and d equals 3, find the first 5 terms. Okay? So I've already given you the first term. Jonathan, the first term is what again? 2. Okay, what's the second term?
Oh, okay. It'd be 2 plus.
2 plus
2
minus 1
times
times 3. Okay? So 2 minus 1 is 1 times 3 plus 2, 5. A sub 3 equals what, Victor?
3 plus 3 minus 1.
No, we're still going with the first term. So this is not recursion. 2 plus 3 minus 1 times 3. 3 minus 1 is 2 times 3 plus 2, 8. A sub 4 equals, Angel, it must be your turn again.
2 plus 3, or wait, sorry, 4 minus 1 times 3.
4 minus 1 is 3 times 3 plus 2, 11. A sub 5, Berkeley.
2 plus, in parentheses, 5 minus 1 times 3. And then that's 4 times 3 is 12, plus 2 is 14.
14, okay, so we said D is the common difference. Do you see 2, 5, 8, 11, 14? You could probably do the next one without the formula. It would be what, Sam?
17.
17. So you can see D is your common difference. Okay, and 20, so you're going for it, okay? So arithmetic sequences are very easy to recognize because you're going to have a common difference between each term. Okay, does that make sense?
So are there times where we may need to be like calculating what that difference is?
There are. Back to the next problem we're gonna do. What if I said I've got 13, 7, -1, -5, ... Does this appear to be an arithmetic sequence?
Yes,
Yes, what's your common difference?
-6.
-6, okay? We're subtracting 6 from each term. The fifth term in the sequence would be -11. Does that make sense? Okay. So could you,
Would there be a positive one, not a negative one? Because 7 minus 6 is 1.
Is the sequence.
Yeah, 7 minus 6 is 1.
Yeah, so it'd be 13, 7,
Oh, you're right.
5, -5.
that's a positive one.
Okay, that's confusing. I was like, huh?
Yeah, sorry, I wrote that wrong. Yeah, that's better. Okay, all right, so now, could you figure out this formula here? A sub n equals, what's the first term in the sequence? I'm gonna have to pick on Caitlin. What's your first term in the sequence here?
The AN. Okay, so the first term of the sequence, is that 13 or 14?
13
Okay,
plus
plus, the n minus 1. So
n minus 1 times
D, which
d
is
is
-6.
-6, okay? I could even simplify that a little bit, right? So this would be a sub n equals 13
Plus, so you would, -6n
minus 6n
plus 6.
plus 6, which would simplify to
That would be 19
19 minus
6n.
6n. Okay? Or you could leave it in that form too, to match. Does that make sense? Okay?
Quick question on so is that the formula we use in any arithmetic sequence, like memorize that?
You definitely want to memorize this formula. Definitely.
Do you want us to simplify it down if you can, or do you want us, or either one is fine?
Yes. Either one's fine. I would, given this, I'd probably simplify it to that, but you definitely want to know this formula by tomorrow. Okay, so let me tell you a true story
About pi.
about pi. This is not about pi. Okay? So a true story. There was a little kid that was super obnoxious. He was in I'm pretty sure it was the 3rd grade. And he was super obnoxious, and his teacher, he was driving her crazy. And she said, okay, mister, I want you to go add the first 100 numbers and tell me the sum. And about 2 minutes later, he came back with the sum, which was 50-50, which was the correct answer. How in the world did a 3rd grader figure this out?
Math.
This 3rd grader went on to become a very famous mathematician, but I can't remember his name. Okay?
Very famous.
Very famous mathematician. Okay? Here's what he did. Okay? He said, well, let's see here. The first 100 numbers, 1, 2, 3, 4, 5, 6, 7, 8, right? And I'm sure the teacher thought this was going to take him a freaking long time. And to be honest, if I was in the 3rd grade, and if I didn't know the trick, it would have taken me a long time. Okay? But then he said, well, wait a minute. I'm going to say 1 plus 100 is 101, right? And 2 plus 99 is 101. And 3 plus 98 is 101. How many pairs do I have? I have 50 pairs, right? 50 times 101 is 50/50.
Wait a second, back it up. Back it up.
Third grader figured this out.
So you're all
Don't get how
good
we
on
checked it, like,
Yep.
did you just see that number? He was like, yep.
A very smart kid, okay? Does it say who is? Oh, it was Gauss, oh yeah, CF Gauss, that was the guy's name, CF Gauss. Okay, now, just so you know, I didn't realize it was Gauss. I should have known that, because Gauss is very famous, and you all know what Gauss is famous for,
Yeah.
because you asked me to do it on every test.
God, extra credit.
The bell curve. He's the guy who figured out the bell curve. Okay, same guy. Okay, so yeah, so he was the one that figured this out. Okay, so that's a freaking smart kid, right? Okay.
But how does that work?
So how does that work? So let me. I thought we were going to introduce that to you today. Well, yeah, we are. I thought it was going to be different though. Okay, so here's how it works. So you've got your properties of sums. Let me add two more onto here. Okay, the one that I just demonstrated is S sub n equals. So this is for. Let me back up. If it's an arithmetic sum. Okay, the sum of, S of n equals your first term plus your last term. Well, they've got it divided by 2 times n. Okay, so if we see this, let's go back to Mr. Gauss, the smart aleck third grader, okay? He said, well, my first term is 1, my last term is 100, okay? So that's going to be 1 plus 100. Divided by 2, that's going to give me 50 pairs. No, divided by 2, and then I've got 50 pairs. Okay? So this is essentially 25 times 101, right?
Is it 100 numbers?
So it'd be 1 plus 100 over 2 times 100.
1 plus, oh yeah, this is 100, not 50 pairs. That's right. The one comes to 100. There we go. I was like, I knew something was wrong. Yes, so you've got your 100 pair, well, you've got your 50 pairs, and then your first term and your last term. Okay? But the thing is, it works not just with integer numbers. So if I gave you a sequence such as, okay, so this works with arithmetic sums. Okay, let's say I had 3 plus 7 plus 11 plus 15 plus, etc., all the way up to 159. Okay. Now the question is, I don't know how many, this leads into the other formula here. There's another formula that we can use here to figure this out, okay? So this would work great because we know what's your common difference in this case. The difference is 4, right? And I know my first term, which is 3. I know my last term is 159. I'm going to divide it by 2, but what I don't know is how many pairs I have, right? Okay. So one of the things that I could do, oh, I've already erased it. Do you guys remember what the formula for the arithmetic formula is?
That's A1 plus n minus
1 plus n minus 1
times d.
times d, right? A sub n, A sub 1. Okay? So in this case, I know everything except for the n, right? If I pick the last term here, so 159 equals your first term, which is 3, plus n minus 1 times your difference. Your difference in this case is 4, okay? So I'm going to subtract 3. 156 equals 4n minus 4, right? Add the 4. 4n equals 160. N equals 40. So I've got 40 terms here, right? Okay. So now that I know that, I can put a 40 here. And then I'm going to get 162 times 20, which is 0, 4, 3, 32, 40. Okay? Now the problem is, what if you don't know what n is? Like in this case, you didn't know what n is. Okay?
I'm confused. Why do we have 40 terms in that?
In this sequence here,
Oh, wait, no, never mind. I got it.
I figured it out.
I took the difference of 159 and 3, thinking it was going by 1. I got it.
Yeah, okay. All right, so there's another formula here that works better if you don't know what n is. Because this formula, if you know the first and last term, you still have to know what n is. And in that case, I didn't know what n was. I had to figure it out manually. Okay? Which you can do, it's just a lot more work. So the other formula that you can do if it's an arithmetic sum is S of n equals n over 2 times 2a plus n minus 1 times d. Okay? Personally, I prefer this one because I can figure this out here. But the idea here is if I substitute this, or rather this, in for a sub n, I'm going to end up with this formula. Does that make sense? Okay. So I've got a sub 1. I forget to put my a sub 1 there. So I already got a sub 1, right? If I add another a sub 1, that's 2a sub 1 plus n minus 1 times d. So these formulas, 4 and 5, are essentially the same formula. It's just if you don't know your n, this will give it to you.
Will I survive if I don't memorize number 5 as long as I memorize the other one?
Yeah, as long as you memorize 4 and this one, which I didn't give a number, 0, I guess. Okay, definitely need to know that one, and you should know this one. Okay, I know there used to be a TV show, but it should be called "Are You as Smart as a Third Grader?"
I was a fifth grader.
Okay, a third grader figured this out.
Or no,
Oh, I get it.
Okay, all right.
practice problem.
Okay, let's do a couple more problems here. Okay, an amphitheater has 50 rows of seats. 30 seats in the first row, 32 in the second row, 34 in the third row. Find the total number of seats. Unless you really enjoy counting. Okay? So, how would you figure this out?
the equation first, right?
Let's set up an equation. Which equation?
So would you do 50 equals, because it has 50 seats.
It's got 50 seats. We want to know the total number of seats, so I'm going to be using a sum. Which of these rules would be helpful?
So the number is going to equal.
So we want S sub 50, correct?
Yeah.
How many rows do I have? 50 divided by 2 times
Uh,
2, which is A sub 1.
A sub 1 is 30.
Got 30 seats in the first row, plus
50 minus 1.
minus 1 times, common difference is 2.
2.
30, 32, 34, 36, etc. Yes,
Is that an S?
S for sum.
Yeah. I think there were 5.
So yeah, this is the S for sum. So typically we use S for sum. We're going to use A for arithmetic sequence. Okay? All right, so this works out to be S sub 50 equals 25 times 60 plus 49 times 2 is 98. So that's 25 times 158. And as everybody knows, that is 3,950, which was a whole lot faster than counting them, which is what you would have done if somebody asked you to do that, right?
Probably.
Or you would have listed out all 50 rows and added them together on the calculator. Or you would have lost track, right? Oh, was that 32 or 34 rows? Or 33? Okay? Does that make sense? All right, one more, and then I'll let you go. We'll keep that there. Oh, except for we were off camera for that whole problem. It was the worst cameraman ever. There it is, though. Okay, here we go. All right, let's see here. How many terms for the sequence 5, 7, 9, 11, etc. must be added to get 572? Jonathan, you look like you wanted to do this problem. Right.
Set 572 is equal to.
Say it again.
So if you get 572 equals n over 2 or 1
Yeah, n over 2 times
2 times 5
2 times 5 plus
n minus 1.
n minus 1 times 2. Now it's just a simple math problem, right? Okay. So 572 equals n over 2 times 10 plus 2n minus 2, right? Which is really 8. Okay. So then I can distribute 572 equals 8n over 2. 2's cancel, plus n squared. Right? Okay. Then what?
Then you solve for it.
Then you get to factor it. So I could rewrite this as n squared plus 4n minus 572 equals 0. Oh, buddy. I don't really want to list out all the factors of 572. So if you don't want to do that, what would you do?
See if what?
What'd you say?
Never mind.
Oh, wait.
Would you do a perfect square? What you said?
Pull up the, oh, wait.
Would you do the perfect square method? You could.
You would have to bring that thing back over.
That wasn't the first thought in my mind. You could factor it. I really don't want to think of the factors though. The book did, as I'm seeing here, but that's not how I would have done it. What's the fail-safe way?
Graph it.
That was a good guess, but yeah, it's a parabola. Go ahead and graph that parabola.
Like, so, yeah.
Quadratic formula, right? So negative b, negative 4 plus or minus the square root of 4 squared minus 4 times 1 times negative 572
My mind never goes.
all over 2 times 1. Okay? That's probably how I would have done it.
Can you do
Negative
a
4
perfect
plus or
square?
minus the square root of 16 plus, that's a freaking huge number though, I don't know if that's helpful. What's 4 times 572? 4 times 2 is 8. 4 times 7 is 28, carry the 2. 4 times 5 is 22.
2,288.
So this is negative 4 plus or minus the square root of 2304 all over 2. What's the square root of 2304? It's a nice number, I hope.
What was it? 48.
48, as everybody knows. Okay, so then negative 4 plus or minus 48 all over 2.
So
Where?
So negative 4 plus 48 is
44.
44 divided by 2 is 26. And negative 4 minus 48 is negative 52 over 2, which is negative, oh, sorry, negative 26. This is 22. Okay, so let's think about this for a minute. Does negative 26 make any sense? No, so I'm going to throw that out. It's got to be the 22 terms. Because we're not going to count in the opposite direction, even though Niels wanted to. Okay? So it would take you 22 terms to get that. Okay? Yes.
Just want to say, I tried solving it with only the 4, and then the other formula, it was.
Yeah, it was kind of nice. Yeah. Okay? So you probably will like both of those. Okay, so test tomorrow is going to be all of chapter 7 and chapter 8.1, 8.2. The one thing that I will say, you guys are going to appreciate that we did not cover 8.3 and 8.6 because those are also sequences, and you're going to be lucky that all the sequences are going to be arithmetic. Well, they won't all be arithmetic. They could be Fibonacci or whatever, but it will be less confusing than it could have been. Okay? So I'll try to get the review up as soon as I can, and we'll see you all tomorrow. And you're all going to do all your good homework in chapter 8.1 and 2.